So we welcome Judy Geyer, who will lead us off in the program today. Thank you.
Thanks, Julianne. Hello, everyone, and it's great to see you all again for this course titled Climate Change. What does it mean for Floridians? In our previous two classes, we learned how climate change is going to affect agriculture and our mosquito-borne diseases. And today, we're going to learn about the implications of sea level rise. We are pleased to have Carolyn Cox with us again today. She is the coordinator of the Florida Climate Institute here in UF, and she will introduce Dr. Katherine Serafin, our speaker today. Carolyn?
Thanks, Judy. Welcome back, everybody, and good afternoon. We have a very, sorry, my phone is going off at the worst possible time. So we have the pleasure of Dr. Katie Serafin today, who's going to talk to us about our unique hydrogeological system in Florida. She's an assistant professor in the Department of Geography at UF, and she researches extreme sea levels, flooding, and erosion hazards to better understand how our coastlines are changing and the resultant consequences for people and places. So before joining UF, she was a postdoctoral researcher at Stanford University with the Department of Geophysics and the Stanford Urban Resilience Initiative. She received her master's and PhD in ocean, earth, and atmospheric sciences from Oregon State University in 2013 and 2018, respectively, and a BA in environmental studies from Connecticut College in 2008. So prior to graduate school, she worked at the U.S. Geological Survey St. Pete Coastal and Marine Science Center. So already had some experience in Florida before looping back after her PhD program. So she's worked with a diverse set of individuals, including researchers from a range of subjects, outreach specialists, and stakeholders from state, tribal, and county agencies. So very, very accomplished. And without further ado, Dr. Katie Serafin.
Thank you so much for that introduction, Carolyn. I'm just going to get my screen sharing going really quick and get this set up. Okay, so now I think we should be good to go.
Looks great.
Great. So thanks again for that introduction. I am Katie Serafin. I am relatively new to Florida, having moved here right before the pandemic and the world shut down, really. And I'm so happy to be here today with all of you to talk generally about sea level rise, a little background information about sea level rise and the implications and how it's impacting our Florida coastline. And so I imagine that many of you, I mean, we all live in Florida, so you've probably been to the beach before. I grew up vacationing on the beach in North Carolina, and I watched the coastlines change year after year. And you know, on your next trip to the beach, when you go to the beach, you most likely won't notice a change in sea level rise. You know, sea level is rising globally only about 3 millimeters a year, as we'll talk about, which may seem insignificant to the average beachgoer when you're sitting on the beach enjoying a sunny day. But these small changes over time can have a really big impact on our coasts, especially in terms of flooding events. And so we'll talk a little bit about that today. So we have some really amazing beaches here in Florida, such a diversity of coastline. We have our white sand beaches all throughout the Panhandle and along the Gulf. We have the Nature Coast as well, with beautiful marshes. And then we have these really developed areas like Miami down in southeastern Florida, and also the Florida Keys. So many different, really unique ecosystems and beaches and coastlines all throughout Florida. And so it's no wonder that we want to understand kind of how extreme and changes to average water levels might impact these locations. Beyond the beauty of our coastlines, Beaches are Florida's leading travel destination. Tourism generates billions, there's a typo, of dollars in revenue each year. And coastal Florida in general employs millions of people annually, earning over $300 billion. Furthermore, besides all the money, in the economy of coastal areas, about 76% of Florida population lives near a coastline. And so coastlines are really unique environments that change naturally in responses to waves and water levels. For example, as many of you may have seen before, after storm events, beaches erode, and so the sand is moved to other locations, and sometimes they recover. Sometimes we pump sand onto the beach. We nourish our beaches to make sure there's enough sand there for recreation and enjoyment. Salt marshes and other habitats are in balance with the elevation of the sea, and they'll migrate inland a little bit if sea level rises at low rates. And so these beautiful environments that we want to live and work and play in, they have their very natural ways of responding to increases to water levels. Throughout history, humans living in these environments have been able to adapt to periodic flooding. However, increasing population and development pressures, increases to sea level, like we'll talk about today, and changes to storm events have made these coupled human and natural systems more vulnerable to extreme water level events. So I'm a coastal scientist, as I was introduced, and I study extreme water levels, coastal flooding, and erosion and impacts on people and places. And my research group really focuses on three main questions. And those questions are, what physical processes drive flooding? So sea level rise and other events that we'll talk about today. How might these flooding and erosion hazards change over time? And then finally, what combinations of events matter to people and places? So why do we care about these, and how do we understand those impacts to these people and places? And we do this by we answer these questions by looking at 4 specific research themes. And so the first one is understanding what drives extreme coastal water levels. So there's many ways and pieces, waves and storm surges and tides can combine to increase water levels. And so we look into understanding how those affect areas now and how they may change in the future. We also think about compound flooding hazards. So along coastal locations, when you have big storm events, you could have high river water levels, a lot of precipitation generating flooding, and then ocean flooding, and how do all those pieces combine to exacerbate flooding in areas. We also think about sea level rise induced flooding hazards. So how small changes to sea levels kind of increase flooding. And then how all these pieces, how they impact people and places. And for today's talk, I'm really going to generally talk about sea level rise and mostly focus on these two in thinking about sea level rise induced flooding hazards and impacts to people and places. And if you're interested, I could always come back and talk about a different research theme, but those will be my 2 pieces today. So before we can really get into how sea level rise might impact the places we love and care about, we first have to know a little bit more about sea level rise and coastal water levels in general. So today we're kind of going to go through a few focus questions of what is sea level, how is sea level changing, and how will sea levels continue to change? And then how are these changes impacting us and our coastlines, and specifically a few examples in Florida. So if we start with this first piece, what is sea level, right? What even is sea level? We talk about sea level, we maybe imagine some average, flat, relative surface, right? I mean, we live in a world where elevations on maps are sometimes given in units of sea level, indicating that sea level is somehow permanently fixed in place. right? I've been to Badwater Basin in Death Valley National Park, which you can see on the lower left-hand corner. I don't know if anyone here has been there before, but it says it's 282 feet below sea level, that location. And I don't know if anyone recognizes the steps on the right-hand side. It says 1 mile above sea level. If you know of a city that is known to be a mile above sea level, it's in the Denver Capitol State Building. And then we even think about our highest mountains in relation to sea level. So Mount Everest is 29,000 feet above sea level. But the fact that sea level is fixed is really, nothing could be further from the truth, right? If we've been to the beach before, you know that sea level is constantly changing. If you were to go out onto a beach and measure where the height of the sea level was for every year, you'd see this really regular signal of high tides and low tides driven by the gravitational pull of the moon and the sun. And so that's just what those squiggle plots are on the bottom of the screen. It's these tidal oscillations over time with an image of high tide and low tide. And these are pretty well predicted because they're impacted by, or they're driven by, this gravitational pull of where the Earth and you know, the location on land is relative to the sun and the moon. But if you've also ever been to the beach on a stormy day, you know that large waves and storm surges can also really increase sea levels, eating away at sand and flooding homes and infrastructure such as roads. So sea levels can change at really short time scales too. Those are probably the most visually obvious changes to sea level that we can think of that happen on you know, daily to hourly scales. But there's also these really large scale regional changes that are conditioned by certain climate conditions. So this is just a figure from 2015, a day in October, of the daily sea height anomalies, showing in areas where red sea levels are higher, and this is the equator over the Pacific Ocean, and blues sea levels are lower. And we can see that there's a lot of variability in this snapshot of what regionally sea level rise or sea levels look like for this given day. And so these kind of large scale climate conditions can change sea levels over decadal scales. So, you know, interannual, over years and longer. And then finally, some of the changes we're talking about today, you know, are really these longer term large scale changes, where this figure really shows sea level from 20,000 years before present. So from the last glacial maximum all the way to present. And it shows how much sea level has really changed over 120 meters since, you know, that time period 20,000 years ago. And this, these are reconstructions from corals. And what we can see is that there's also very different rates of sea level change over time. Whereas over the last, you know, from present to the last 6,000 years or so ago, sea levels were relatively constant and compared to these other time periods between 20,000 and 8,000 years ago. And so that's when we really industrialized and started to you know, technologically grow and develop our coastlines in these periods of stable sea level. So as you can see, there's many different drivers of sea level, and we'll dig a little bit into exactly how those different pieces change sea level over different terms. But you can see there's short scale and longer scale drivers. But sea level, when we talk about sea level, we talk about an average, even though we know all these processes and things are changing sea level over time. And so at the coast, we know how sea level is changing because we have tide gauges that are at different locations on our coastlines that measure how high the water level is. And our earliest tide gauges were put in about the 1800s. And we see from those tide gauges that on average, sea level has risen about 2 millimeters a year from 1900 to present. Since the early or the late 90s, we also have satellite altimetry data. So satellites that are, rotating around the Earth can also measure the average of the sea surface all around the globe. So we're not just limited to these specific coastal locations. And with those, we see that on average, sea level has risen approximately 3 millimeters a year from 1993 to present. And these satellite altimetry measurements and the tide gauge measurements, which now are combined on this left-hand plot, really line up together, showing this consistent trend of sea level rise in our recent history. And this average across the sea surface from the satellite imagery and averages across all of those tide gauges is what we call global sea level. And global sea level is a spatial average over the entire ocean from these measurements. And so when we think about global sea level, that's usually when we're talking about sea level rise, the numbers when climate change reports and IPCC reports come out are giving us numbers in projections of global sea level rise. So when we think about global sea level change, we have to think about what might drive that global sea level change. We want to ask the question, well, what might change the ocean as a whole? And usually a good way to think about this is, instead of thinking about the ocean, thinking about a bathtub. So if you have a bathtub, there's only a few ways the water in that bathtub can change, right? You either have to increase the amount of water in the tub by turning on the faucet. You can decrease the amount of water in the tub maybe by opening a drain. Maybe if the temperature changes in the tub, the water height will change in the tub. And then this is a little bit more difficult, but if you were to increase or decrease the size of the tub itself, right, increase the volume of the tub, the water would change. And so those are kind of the four mechanisms and ways that global sea level actually can change too. If we think about turning on, adding more water to the tub, that's melting ice. That's like melting all of our ice sheets. If we think about decreasing the amount of water in the tub, so opening the drain, that is storing more water on land. If we think about changing the temperature of the water in the tub, that's an analogy for thermal expansion. So how the volume of water physically changes depending on its temperature. And then an increase and decreasing the size of the tub, which we're really not going to talk that much about today, is kind of analogous for seafloor spreading. So from plate tectonics, we can physically change the volume of our ocean basins. So to understand, I'm just going to go briefly through each one of these processes. And to understand these first two, of melting ice and land water storage, we really have to understand the water cycle, which describes a continuous movement of water on and above the Earth's surface. So the mass of water on Earth remains fairly constant over time. But during cold periods, we have more water trapped as glaciers and ice sheets. And then also, water can be stored on land in rivers, lakes, and groundwater. So when we look at these drivers of global sea level change, if we melting ice, when glaciers and ice sheets melt, they release large volumes of water back into the ocean, which increases sea levels. And so this is something that we've been seeing since we've been able to measure mass volume losses of our ice sheets on Antarctica and Greenland, this steady decline in ice mass across these different locations. And so the red colors in the two ice sheets of Antarctica on the bottom right-hand side and Greenland on the bottom left-hand side just show the areas where it's been losing the most mass since the early 2000s. And this is really one of the main contributors to the sea level rise we're seeing at present. The next driver of global sea level change is land water storage. And so, like we said before, that's when you trap water on land in lakes or rivers. And as humans, we've done a really good job of doing that by building dams. And so over the 1970s, where we had kind of the largest increase in dams, if you look at records of sea level, we actually saw slight sea level slow down in rate over that time period because of how much water we were trapping up on land in dams. So dams impound water and decrease sea level, while something like groundwater depletion, so when we're using groundwater at an active rate, it means more water ends up in the oceans. So we add to sea level rise when we use up groundwater. And so you kind of have these two different processes with land water storage. And then this final driver of sea level change that we'll talk about is this thermal expansion. So really, as water heats up, it expands and it takes up more volume. And so which means it increases in elevation. And so here I just have a map, a figure where red color is warmer, blue color is cooler. And this just shows the seasonal cycle of temperatures at Clearwater Beach in Florida. This was pulled from a Florida wetsuit guide for those who want to get wetsuits and maybe go surfing in this area. But we can see we have the warmest waters in the middle of the summer in July and August, and then our water temperature drops throughout the winter. And so this thermal expansion isn't just something we see over these really long-term timescales as temperatures rising, but we see it as very local signals too. So for example, here is our seasonal signal in temperature at Clearwater Beach. And I know the text here is a little bit small, but if we look at the same monthly measurements of the average elevation of the sea level in Clearwater Beach from a tide gauge there, you can kind of see a similar, maybe a little lagged trend of sea levels are physically higher, even if slightly, over the summer and fall periods than they are during the winter. And so these are three really important, the main drivers of sea level change over our whole ocean when we're looking at global sea levels. And we can kind of other researchers have pulled apart what's contributing to these changes that we're seeing. And here the black line over time is just the global sea level from satellite data that we looked at earlier. The blue line is what's been added mostly from meltwater, so increasing sea level due to melting ice. And the red line is thermal expansion. And when you add those two together, you get the purple line, which matches up very nicely with our observations. And in recent years, the largest contributor to sea level rise is from ice melt, while thermal expansion maybe causes a third or less of global sea level rise from the early 2000s onward. So all of these are very important processes and kind of what we are the main drivers of sea level change. If we look at how this specifically relates to Florida, which you can see on the map on the right-hand side, these are estimates of sea level rise at specific tide gauge stations around Florida. And the green arrows represent a sea level rise change of 0 to 3 millimeter a year, which is about the same as the global average. And a yellow arrow indicates sea level rise trends of 3 to 6 millimeters a year. So that's a little bit above what we're seeing the global average is. And so while Florida, most places in Florida are rising at rates of the global sea level is, that's not the case everywhere. If I were to zoom out and show you a map of the entire United States, we can see that there's some locations where you have these really red arrows, like in Louisiana and Texas, which means that sea level is rising much, much, much faster than the global rate. And we have other areas where there's purple and blue down arrows pointing down, and that means that sea level is actually decreasing. And so sea level rise at specific sea level change at specific locations might be very different than the global averages. And this is because there's a lot of regional factors that drive local sea level changes on top of global sea level changes. And so we term this, there's a distinction between global sea level, where we assume is affecting everywhere at the same rate on average. And then site-specific places have a relative or regional sea level change that can be much higher or much lower than the global average. And this is what's really important to understanding impacts in coastal areas. And so this variability, I'm just expanding this map even more just to show, I know it's really zoomed out, but more arrows around the world. But there's a lot of variability in sea levels everywhere that we have these tide gauge measurements. And this variability, this very local scale variability, is driven by vertical land motions. So I'm just going to briefly list these and then we'll go through them. Water mass changes and winds and currents. So very much more site-specific features. And so vertical land motions, as they might sound, really is just that land can be moving relative to the sea. And that means that it can either increase or decrease sea level. So those locations in Alaska where we saw that sea level was falling, that's really because plate tectonics there, we have a very active coastline and the land is rising. So if the land is rising, it will look like sea level is falling. We also can get very intense higher rates of sea level rise in places like Texas and Louisiana from sediment compaction. So the land is sinking because of all of the oil and water we've withdrawn from the ground in those locations, which means this not only is global sea level rising, but the land is sinking, making sea level look like it's rising even faster or in those different areas. The next, which is a little hard to wrap your mind around sometimes, is changes to water mass. So when ice melts, when we have these huge ice sheets on Antarctica or Greenland, for example, or even what was over the Northern Hemisphere when there was an ice age, when that ice melts, it's relocated to a new area. But you can imagine when you have such a heavy piece of ice sitting on land, it has a gravitational pull. And so what happens is that when you have an ice volume, it's pulling the water near it to it. And so when that ice volume melts, you actually have a fall in sea level at that location because you're reducing the gravity pulling the water to the ice sheet, and you have an increase in sea level in other locations. And what this means, this is just a map that shows us across the world if some ice sheets in Greenland and Antarctica were to melt, that sea level rise isn't necessarily distributed everywhere equally, because around Greenland will see sea level fall. Around some areas of melt in Antarctica will see sea level fall. And then you see a large redistribution of water rising over the equator and some other areas. And so there's a redistribution of water itself across the ocean that is due to how much ice is on land pulling water to it. And then the final driver of relative sea level change is from winds and currents. And so, like we talked about looking at these large scale anomalies very early on, when you have wind and changes to climate, you could change the way the wind blows and the way currents move. And those patterns can shift the elevation of the water level itself. And so sea levels can be enhanced in some areas, or sea levels can be suppressed. And so these are all the many ways over a global scale or over a regional scale, sea level can change. And so you can kind of start to imagine why it's potentially so difficult to predict what sea level might look like in the future, especially at a specific site, and why there might be such large ranges in projections of sea level rise in the future. And so when we start to think about estimating future sea level, it's actually easier, it's not easy, but easier to predict changes to global mean sea level compared to regional or local sea level at a specific location. And why is that? Well, like we just talked about, there's really a lot of different processes that can affect regional sea level that change on much shorter time scales, like changes to winds and currents and decadal cycles. And when we're thinking about this global mean sea level, we only need to worry about, two main processes for at least projections into 2100 and beyond, and that's adding water to the ocean and warming the ocean. And so a lot of the projections that we'll see are really future global sea level rise projections. And so if you've ever looked at sea level rise projections, this figure might look really familiar, where here we're looking on the x-axis, it's just our year. The y-axis is our change in sea level in feet. The black is our historical, so we've looked at a few of those from our tide gauges and our satellite data. And all different colored lines are projections now out into 2100. And we see this wide range of about, 0.25 to 2.5 feet to 2100 for global sea level. And those large ranges are driven by different dynamicals. So, modeling the dynamic processes and the physics-based processes of all of these interactions that we just talked about, or statistical modeling, and using past observations to think about sea level rise in the future to constrain future sea level. But there's a lot we don't know about, for example, how ice sheets might melt, which gives us this very, very large range. But as we talked about, this may or may not be specific to our Florida coastline, right? Right now, our Florida coastline looks like it's rising, sea level rise at a rate that's about average or is similar to the global sea level. We know for sure these projections might under or over predict sea level rise in other locations. And so others have also started to estimate regional sea level rise scenarios. So taking those global sea level rise curves and trying to contribute these local scale processes like we just talked about to be able to create these different changes to sea level for specific coastal locations throughout the US and throughout the globe. And so this is a recent methodology developed in 2017 by NOAA, the National Oceanographic and Atmospheric Administration. And we can see on the upper left-hand corner is the low global sea level rise scenario, but in the regional projections. And then the bottom right-hand corner is our extreme, so that the highest sea level rise scenario possible. And you can see that there's a lot of variation, that places like Alaska and Oregon and the Pacific Northwest coast, you actually have for low global sea level rise scenarios, you actually have regional sea level rise that is falling just because of the land movement in that area. And then in some locations, like along the Gulf Coast and Florida coastline, you have rates of sea level rise during these projections that are very similar to global sea level rise or even more. And so I just wanted to quickly zoom in on 2 Florida locations from these sea level rise scenarios. And this is for Pensacola. And actually, because a lot of sea level rise across Florida is pretty similar in the different projections, these two plots look very similar. But each of the dots throughout time represent a different sea level rise scenario. So the purple and bluish colors are low sea level rise scenarios, and the pinks and red colors are very high sea level rise scenarios. But we can see by mid-century, this projection of local sea level in Pensacola is about 1.5 to 3 feet. So having an uncertainty and a range of that amount of rise by 2050. And when we get all the way out to 2100, we're looking at potentially 4 to 10 feet of sea level rise when you go out to the really, really extreme end scenario. If we look at Cedar Key, so I just pulled another of the stations on the Gulf Coast, but kind of, close to our backyard. We have very, very similar projections of sea level. And so I know that I spent a little bit of time going through all these different drivers, but I just wanted to show kind of the complexity of what's actually driving sea level, and especially since we hear about it so much in the media and in the news on impacts, we can start to reflect when we're given either global or relative or sea level rise rates, what's really important for the place that we are in or at. And so just to, obviously, there's kind of like a break now in the themes where that was just kind of a general overview of the processes driving sea level. But now I want to get into more kind of the local impacts of how sea level actually is impacting some of the locations we might love and care about, and how it's impacting and changing our coastlines. And so the first thing that we have to think about is really, how does sea level rise alter flooding hazards? What sea level rise does is it exacerbates short-term events first and foremost. So for example, when we have an extreme event like a hurricane, right? A hurricane, basically when it's moving to shore, its winds blow water up onto the beach. And so that is one component of storm surge, just the wind blowing and pushing water. But the storm itself also exerts a pressure on the ocean, and that pressure creates a bulge. So the wind blowing and the pressure bulge both contribute to those large storm surges that flood out an area. And what that does is, if you look at a tidal oscillation here in black, and then you add a big storm event on top of it, it can increase the elevation of our water level by many, many feet or meters. And so for an extreme event, sea level rise would push that storm impact slightly higher and be able to reach inland further, exacerbating storm events. It also means that smaller hurricanes or smaller storms might have more of an impact than they did when sea levels were lower. The other way sea level rise can alter flooding hazards is by changing the average event, so pushing tides slightly higher and causing something that previously wasn't a flood. And so this schematic just shows what our tidal oscillation would look like in black in a past sea level condition. And the orange line across the top is a threshold. Maybe that's a sewer being flooded, or something that's indicative of flooding. And with just a little bump up in sea level, even without a storm event, you can push your tide events higher, which now means that area that didn't flood during high tides now does flood. And so that's something we're gonna just briefly talk about. And then the final way that sea level rise alters flooding hazards, which is maybe the one we're most familiar with because you see maps of it pretty frequently, is permanent inundation of the coastline. And so when you have like 1 foot of sea level rise, I think this is a very extreme, I think I put 6 feet of sea level rise here in the Tampa Bay area just to have places really flooded out and inundated. You know, that means that those locations are underwater and we will have had to move any of that infrastructure that is in those locations or it would have flooded out. And so that type of impact really is longer term inundation for and what we should be thinking about planning for. But it's these shorter term impacts like changes to extreme events and changes to average events that are most impacting our coastlines right now that we are starting to deal with it. The repercussions of. Oh, forgot I had those little. So I'm just briefly going to go into some of my own research on sea level rise induced flooding hazards. And I wish that I was with all of you because I feel like I've just been talking and I'm unsure of how to interact, but I don't know if I see some of you on camera, so maybe you can raise your hand. But how many of you have heard the term before, sunny day flooding? I see a few hand waves. What about high tide flooding or king tide flooding? More hand waves. And then nuisance flooding? See some thumbs up. Yeah, so these are becoming really common, more common, and we're hearing them about them a lot more. And, you know, maybe when we break, I would love to hear about your own experiences if you have experienced this type of flooding. But what we're seeing in Florida is that, and in many places, that we have this increasing amount of flooding during sunny days. And that's related to this fact that our baseline sea level is higher. And so these tide events can push its way inland a little bit faster, or sorry, higher. And so they're also referred to as nuisance flooding or high tide flooding, and it's low levels of flooding which have the potential to disrupt daily routines, put added strain on infrastructure, and cause minor property damage. And we're used to thinking about overland flooding, right? Flooding coming up and inundating, coming up over dunes, inundating roads, big storm events. But the interesting thing about nuisance flooding and these you know, small sea level rise driven changes is flooding can start to come up through infrastructure. So you see water bubbling up through drainage systems that usually outflow into the water, but now into the ocean, but now instead of storms draining out, high tides are draining in. And then you can also have changes to the groundwater table, which causes flooding inland without any type of overland flooding. And we know that these are directly related to sea level rise. We've seen an increase in these minor and nuisance flooding events over time that are directly correlated with sea level rise. I know this is a little bit of a messy figure, but here we're looking at tide gauge stations all up and down the East Coast. And this 3D plot here kind of shows each of those tide gauge locations over time and the days per year that we see these minor flooding events occurring. And what I want you to take home from this figure is that when we look towards presently, there's a lot more red. So there's a lot more days per year that they're happening. They vary year to year due to large scale changes in weather conditions and ocean circulation. And because we're going to continue seeing sea level rise, they're expected to continue into the future. And so these are characterized as nuisance flooding events because they're annoying, right? They're not necessarily causing the same amount of damage as a huge hurricane would, which might erode dunes and flood out property.
I think I might have an appointment I need to cancel on Thursday.
But imagine if the road outside your house was flooded for 3 months straight.
Yeah,
that happened in
back. Okay. Yeah, if you would. Okay, is that
just have a little bit background. That happened in the Florida Keys in 2019. And so we had this issue where in the fall, there were roads that were flooded out for almost 3 months straight. So this last piece I'll talk about is, and I realize I need to wrap up, so is thinking about how we can better understand how severe these events could be, not just by counting how many days a year a water level might reach a threshold, but thinking about how long that flooding event may stay over that threshold. And so what we're doing is looking at tide gauge records across the United States. And so here I'm showing you the longest records. That's what this analysis is being done on. And this is an example of Cedar Key, where we're looking at when we have a minor flood event, how long it stays over that minor flood threshold. Because you can imagine something that is 2 hours long might not have as much of an impact as something that's over 5 hours long. And so what we're trying to understand is, first, how long, when we do cross over this threshold, is flooding kind of sticking around, and then later hope to explore what kind of impacts that might have on people and places. So we can look at this for the entire United States. And what we see is that this proportion, so here I'm showing a pie chart which shows the proportion of flood events that are short duration in this blue, medium duration in teal, and long duration in yellow over time. And so early on in our record, we had from 1930 to 1960, much fewer events and less proportion of long duration events than we have now. Because if we look at present day flooding from these same events, we can see that we're getting more long duration events now, especially in the Gulf, so these yellow events, and we have a much higher amount of these events occurring, as has been shown in other projects. And so we find that the majority of these stations are dominated by increases to short duration events, and that stations that experience the highest frequency of events are often dominated by short events. Furthermore, the flood duration can seasonally vary. So this map, these figures just show a few different stations and when flooding is happening. And I'll just highlight the Fernandina Beach station here, which shows us that most of this flooding is happening in the fall. And a lot of the times this flooding happens is related to tidal oscillations. We have our highest tides in the fall and the spring, and because mean sea level is bumping them up higher, that spatial pattern emerges across a lot of different states or stations with different variability. And I'm sure most of you already raised your hands and said that you've experienced this or you've seen and heard these terms, but there's tons of articles. When we think of what we're doing here in Florida, you know, places like St. Augustine, definitely down in Miami also, are starting to build infrastructure and put in tide valves and other drainage infrastructure that can remove some of the impacts of these flooding events. And so some infrastructure that was just put in St. Augustine in October 2017 or in fall of 2017 shows that they've started to be able to manage some of these flooding events by changing some of the infrastructure. But you can imagine this is likely a short-term fix as sea levels continue to rise. And so just to go back here, I think one of the most important aspects of this work is that these locations that have less frequent but long duration events might be at a higher risk to flooding in the future. And one of the least studied aspects of these nuisance flooding events is that they could be more cumulatively expensive over time. There's potentials for many cascading repercussions, such as commute disruption, which I've worked on a little, business disruption, displacement, public health issues, exacerbation of poverty, which it's not as easy to measure as the damage from this one large event, right? And so it's really difficult to quantify the overall impact of these events, but they're eating away at our economy as they slowly grow, increase over time. And so I just wanted to bring it back to thinking about the diversity of our coast and just wrapping up that sea level rise, it's not a future problem. It's here, and the key is to begin adapting now. There's really not a one size fits all solution. All of our different coastlines are really different. And so, tidal valves aren't necessarily going to work everywhere, because that's not necessarily, that type of flooding isn't necessarily an issue everywhere. And so what we need is coordinated, flexible adaptation strategies, like property buyouts or nature-based solutions beyond just traditional strategies like beach nourishment, to consider our future coastlines. And so just the final summary of this talk is just that sea level rise is driven by a myriad of different processes on global and regional scales. Sea level rise will increase and is increasing the frequency of flooding, especially in thinking about these nuisance flooding events. We don't currently understand all of the cascading repercussions of sea level rise, so kind of coordinated research on all these interacting components is necessary. And understanding all these integrated components of their coastal systems will help us plan equitable and sustainable coastal futures. So with that, I'm finished. Sorry, I went a little bit over, but I'd be happy to take any questions. I see that we already have some in the chat, and as always, I'd be happy to give a talk on a much more specific research theme in the future. Oh, Judy, you're muted.
There can you hear me now?
Yes.
Okay, thank you very much, Katie. It turns out to be a much bigger problem than what you think of in terms of sea level rise, and not as uniform as we have, at least as I had anticipated. Julianne, if you are there, do you want to facilitate questions and the response to chat?
Okay.
I've got on my screen, I've got several chats, and I see.
Yep, I have on hands. I'm going to alternate if that's okay. So let's go to chat first. Do you project a mass migration from coastlines to internal locations? And if so, when?
Thanks for your question, Bill. I cannot answer if so, when. I think that's hard. I think that it's going to be very place-based, in the sense that there are some locations, I think, like big cities like Miami and Boston and New York, that it will make sense to develop, have hard infrastructure, and keep in place for as long as possible, because of how much wealth and investment is in those areas, whereas smaller barrier island communities and other smaller coastal communities will either likely turn into maybe just rental communities, or will have to start thinking about property buyouts and moving inland. So I think that it's my line of work doesn't really look at the mass migration aspect. There are other people who maybe are better suited for that, but I think that there's going to have to be a lot of like policy and flood insurance and mortgage, what types of mortgages are backed on coastlines, and real estate changes to start to motivate some of those actions of migration, at least from an economic standpoint.
Thank you. Anne-Marie, go ahead.
This was just a wonderful talk, and I wish I could have taped it for people that I know who would be interested. But thanking you is one thing. I wanted to ask you kind of a nitpicky question, possibly for you, but not for us citizens out here. And that is, in the coastal science community, are the terms that are used, they're kind of odd terms, king tide, nuisance flooding. Are they seen in the coastal science community as an attempt to normalize or sidestep the political fallout of what is essentially a global climate change trend, and trying to avoid human actions? I just wonder if people in the coastal science community ever use those terms.
That is a great question. And yes, because it's a newly defined emergent phenomena. So in the coastal science community, we use all of them. And there recently, a few years ago, was a paper that came out that was called "What is Nuisance Flooding?" And I think nuisance flooding overall refers to this low level of flooding, but it doesn't have to be coastally driven. So you can also have nuisance flooding from precipitation events, where you just have a lot of, we all know, we all live, we live in Florida. There's some areas that maybe don't drain as well as other areas, and it's not necessarily related to coastal sea levels. And so I think that's why nuisance flooding is maybe a more all-encompassing term of these flooding events that I don't know if it's as well defined, because it makes it seem like it's an annoyance, but for some people over time, they might be very, catastrophic is maybe not the right word, but they might be very, very detrimental and kind of hurt this kind of social fabric of communities. I think that the king tide is specifically related to those high tide flooding events that now are pushed over that baseline. And I think sunny day flooding came about from the fact that, especially in Florida, we're getting flooding from non-storm events. And so scientifically, I use them all. I prefer nuisance flooding, but I think that the explanations came about as ways to communicate this new emergent complicated phenomena. But I love, like you said, we could probably talk about this for another longer time, but I think it's, trying to show people that it's not just storms anymore that cause flooding.
Right.
Thank you. Bob, go ahead.
Can you hear me okay now?
Yes, go ahead.
Okay. Two comments that maybe you could comment on. One observation, you showed it in your maps that sea level rise is not just a coastal phenomenon, but it extends all the way up to as far as tide reaches. For example, Tampa Bay, Indian River Lagoon, extends up to Washington, D.C. So that, and where I lived in Palatka, it was a hard time convincing county commissioners that because the river was tidal there is subject to sea level rise and that you need to prepare for that. That's one observation. The other is one that I struggled with for quite a while and talked with physical oceanographers. But another driver actually is ocean currents, at least locally. There's a seasonal phenomenon that along the east coast of Florida, average water levels in October, November are probably a foot or so higher than in July. The best explanation I can get, and you showed that the Gulf of Mexico is about 4 or 5 inches higher in the summertime than in the wintertime. And that high water, of course, water flows downhill, it goes out the Florida Straits up the east coast. And as it flows, it's the Gulf Stream, or it's really the Florida current locally. As it flows fast, this Coriolis acceleration, or from the Earth's turning, tends to curve currents to the right and pull water away from the coast. As it slows down, the water levels rise. And there are other phenomena, apparently melting of Greenland glaciers that are slowing down the Gulf Stream. And that might contribute to regional sea level rise. And it's a big deal. I mean, a foot difference is in flat Florida is quite a deal. I wonder if you'd commented on either of those, the inland aspect of sea level rise and the seasonal aspects just from currents.
Yeah, both great comments, questions. To hit on the first one, actually the compound flooding work that I do focuses on thinking about river systems, coastal river systems, and how both changes to precipitation and river discharge and changes to ocean boundary conditions, we're trying to define where both processes matter, ocean and river, for generating high water level events that we might be mischaracterizing, and how changes in climate to both aspects might also alter that kind of in-between region, and in what ways, depending on the strength of the drivers. So I have a research project right now. We're looking at the Suwannee River and some other rivers around Florida to think about how can we efficiently model some of these systems to look at this, and then what types of climate drivers might change the contribution or interaction over time. And so, I think that that's like you're saying, there are a lot of people who do very specific site-specific estuarine dynamics of locations in that tidal influence upriver, but we're looking at a small piece of that as well. I will say, like I said, I am new to Florida specifically, and so I'm still learning all the current systems and the impacts to regional water levels. I have a graduate student who'll be looking at extreme water levels all throughout Florida, but I did a lot on the west coast of the United States, thinking about currents as well, and changes and seasonality. And I mean, you're right, you have all these different pieces, these very dynamic pieces that are increasing and decreasing sea level, that happen within a year, that happen, over longer scale times, so maybe tens of years, and then all of a sudden a current shifts slightly and drops sea level in a place. And I know there's other researchers at UF who have been specifically looking at kind of Gulf Stream and sea level hotspots on the east coast of the United States too, and Florida, and how those processes interact. But I think it brings up the point of how complex this can be to model into the future, that you need those dynamic models that can look at these processes, but then they're also computationally expensive, and there's some of the physics we don't quite understand all the pieces of.
Thank you. Barbara, go ahead.
Thank you for a very interesting and informative presentation. I'm sort of sorry your work is confined to scientists, because I think the general conclusions that you have drawn and given us today would be most important for the general public. So my question is this: has there been any attempt made to connect the kinds of conclusions that you're drawing, such as that sea level has been rising and will continue to rise, with trying to educate the public on those things that cause sea level to rise? I'm talking about climate change and some of the things people can do to try and change their behaviors. I was particularly taken by that picture you shown of St. Augustine, where you showed the flooding street and then the cleaned. To me, that might give people the wrong impression. Okay, we got this fixed, rather than this is just, as you said, a temporary solution, and these problems are going to continue. So to connect the kinds of things you're doing with trying to get the public to change their behavior, has there been any move in that direction?
That's a great question, and I agree with you that there are some of these short-term fixes that we use that are great, because they remove some of these problems, but then we kind of say, oh, that's fixed now, well, we'll just deal with it. And I think that we might eventually start to move to we're going to have to live with frequent flooding or live with water if we want to live in these locations. I think that, so again, yes, I think that there are efforts. I know UF has, that Carolyn Cox actually is a part of, but has some courses that maybe work with some local communities. And I know that there are projects that are ongoing. And I am working to create partnerships with local communities too, and outreach. I love opportunities like this, but like I said, I only moved here kind of when everything shut down. So I'm still building those connections. When I lived in Oregon and in California, we did a lot of research for and with local communities, guided by local communities. And I think some of these problems that we talked about, for example, understanding how nuisance flooding really impacts communities, it's the people who live there that can answer those questions. And I think we need to, in the science world, utilize that relationship a bit more and be learning with each other and from each other to kind of take the science and make it more insightful for action. But I think that there are groups and people who are deeply involved in outreach. I know Florida Sea Grant is a great extension agent as well across the state. I am working to build those connections. I plan to, so it is something that I feel very strongly about. But so I hope that answers your question a little bit.
Thank you. And Richard Petway, you asked to be addressed?
Yes, I have a question that's maybe out of your purview, but I'm interested in the interaction between sea level rise and the fish supply, or even if it's just related to coastal, like oysters and mussels and that kind of stuff that's coastal products, or does it actually have more impact upon fish populations off the Grand Banks, for example, or off of Florida in deeper water?
So I can't answer that question specifically. I think that I heard that next week, is somebody coming to speak on fisheries, or was that last week?
Yes, correct. Mike Allen from the Nature Coast Biological Station will be here next week.
Right, because I know something like
He
oysters.
may be,
Sorry, go ahead, Judy.
I was going to say, he may be able to more specifically answer that question, Richard.
Thank you.
Yeah, so kind of deeper sea. Sorry, Richard.
Thank you.
Yeah, I was just going to say that for oysters and more intertidal or species, obviously that depth of the water matters a lot, and the in some locations the amount of fresh water or seawater, salty water matters a lot for habitat also, and potentially fish stocks in coastal locations for I think juvenile fish. But like we just said, I think that next week Mike will be able to answer that question more specifically than I can.
Thank you.
Okay, just a moment. There's one more question here in chat, and Judy, you have a question in your chat, if you can look at it.
Okay, and I wanted to make the comment about from Carolyn Cox too. Do you see that one?
I do not see hers.
Okay, I want to have that one come in. Excuse me.
Let me ask this one real quick. Are there any studies of worldwide geopolitical and economic impacts of flooding?
There are definitely studies that have looked at the amount of people who live on the coast or in coastal locations, and large sea level rise increases and potential impacts to GDP. But obviously these are kind of coarse resolution, just to think about like large scale overlaying of water levels onto landscapes and things like that. And a lot of times it's hard to predict kind of how infrastructure and population will be changing on the coast. So when we say, if we want to look at 6 feet of sea level rise into the future, well, what our coastlines are like right now might be very, very different than once sea level has started to rise in population. And so yes, studies do exist, but I've worked mostly on more local scales, and so I can't give you exact numbers off the top of my head about what the impacts of that would be, but they're high.
Okay, Judy, if you want to finish up.
Right, we're running close on time. There's going to be another program in the Oak Room at 3 o'clock that Julianne has to set up for. So I'm just going to read a comment that came from Carolyn Cox to everyone in answer to Bill Rossi's question about whether we project mass migration from the coastland to internal locations. And she writes, it has already begun in Florida. As soon as the National Flood Program accurately prices risk, people will need to move as they will not be able to afford insurance. Cash buyers will stay as long as infrastructure remains viable. And I can tell you, after having talked, not very recently, but within the past year with Nikki Doria in our marketing department, that we are getting inquiries and visits, or we're getting visits from people in the Miami area who are trying to sell their homes and get out now while the getting is good, so to speak, while they can do that. And I'm very sorry, but I have a question here that came from one of the people, Pat Harden. And what I'd like to do, Katie, is send it to you and have you answer her directly, because we've run out of time and I have to give Julianne the space to get ready for the next program. So thank you all very much for attending, and thank you, Katie, for a very informative and important program, as Barbara mentioned. We'll look forward to hearing more from you in the future. Thanks again. Bye-bye, everybody.
Thank you. Bye, everyone.
Bye, thank you so much.